Hello everyone, here we'll be discussing tangent planes and linear approximations. To be quite honest, we mostly want to discuss tangent planes. Linear approximations are exactly what you know them to be from Calculus 1, but now we're just going to be dealing with things with a function over two variables opposed to one. So it's kind of the same idea, just using tangent lines, in this case tangent planes, to approximate a value of a function given a value on the line, or in this case tangent plane, near that point. But anyways, let's just discuss here what the whole deal is in regards to tangent planes first, and then we'll discuss linear approximations a bit. So here I say if f has continuous partial derivatives, then an equation of the tangent plane to the surface z equals f of x comma y at the point P, which is x naught, y naught, z naught, is given by this following equation. So I say unequation because, of course, you can manipulate this to get it in different forms. But I want to say this is basically the main way of writing the equation. In fact, this really reminds me of slope-intercept form. If you think of y minus y naught equals the slope times x minus x naught, this is completely analogous to that. But notice here, we have these slopes. Let me kind of highlight them in green here. In the x direction and in the y direction. And notice we're evaluating these partial derivatives at the particular x and y values of this point. Of course, f is a function of x and y, so it's only fair that we plug x naught and y naught into the partial derivative function to get the slope in the x direction and the slope in the y direction. And then adding those basically, or I guess using those as basically components to the normal vector of the tangent plane is basically what's going on, we end up getting this nice tangent plane. So I know it sounds a little funny, but just again, imagine you have some surface in 3 dimensions, something like this. In one direction, at a particular point, you have a tangent line in one direction. Let's say this is in the y direction. And then you have another one in the x direction. So notice these are each fx and fy at that particular point. So in other words, plug in an x naught and y naught. But if you consider both these at the same time, really what they kind of combine to is uniquely identifying this plane. So these two lines that are not parallel, they intersect at this point, can actually define this plane. So if you kind of imagine me trying to draw this plane here, and this plane will be the tangent plane to this curve that I tried to draw in black. So in other words, it is analogous to what we consider the tangent line on a function in 2 dimensions, but now over a surface in 3 dimensions now. So instead of tangent line, now we have this sort of tangent plane. All right, so now I want to kind of discuss the language a little bit. So I say if partial derivatives fx and fy exist near a point a comma b and are continuous at the point a comma b, then we say that the function fx comma y is differentiable at a comma b, which I know is kind of funny to say, but really if fx and fy exist, then we can say that this function is differentiable. In reality, they need to exist at most near this point. They don't really need to exist at that point, but that conversation gets a little technical as it turns out. So now I want to, erase this and then do an example where we actually find the equation for a tangent plane of a given function of 2 variables. Okay, so here we have this example, and then afterwards we have this follow-up question. Here we're asked to find the equation of the tangent plane to the elliptical paraboloid z equals 2x squared plus y squared at this particular point, 1, 1, 3. Now, if you don't remember, we discussed elliptical paraboloids in the past. An elliptical paraboloid is exactly what it sounds like. It's this kind of 3-dimensional parabola where the cross-sectional image is it's an ellipse. If the cross-section image was just a circle, then it's a circular paraboloid. Now, paraboloid just literally means 3-dimensional parabola. So it's literally what you describe as a parabola, but kind of in each direction in 3 space. So this is kind of the image we get, kind of. And what we're asked to find again is this tangent plane at this particular point. Now notice here we usually let z be f of x, y, just like we usually let y be our f of x in usual functions of 1 variable. Here we have, of course, a function of 2 variables. So this is our f. And it wouldn't be a bad idea to ensure ourselves that if you plug 1, 1 into this function, you indeed get 3 as your output. And clearly it's the case. So I'll let you figure that out on your own, of course. But now, remember that to find the tangent plane, we need to first find fx and fy. So let's first find fx and fy. So fx, I'm just going to write as fx, and fy, I'm not going to write the x comma y input part of it, just for space. Now derivative of this with respect to x only is 4x, where derivative with respect to y only is 2y. And remember, that's just regarding the opposite or other variable, in this case y, in that case x, as a constant, and we get these results. And now plugging in the x and y values of our particular point that we want to find the tangent plane of, or at, then we'll plug in and we'll get of 1 comma 1. When x is 1, this is just 4. So let me circle this result. And when y is 1, for this function, we just get 2. Perfect. So now all we need to do is just kind of use the equation we saw on the previous screen. Let me erase this just for space here. And recall that the equation was super similar to what you remember point slope form to be. So that is, let me kind of move this out of the way too. And that is, of course, z minus z naught equals fx at x naught comma y naught times x minus x naught. And then similarly we have fy at the point x naught y naught multiplied now by y minus y naught. And considering this as our x naught y naught z naught, and fx of x naught y naught to be this, and fy of course to be the other value, we get the following. Z minus 3 is equal to 4 times x minus 1 plus 2 times x minus 1, y minus 1, sorry. So I hope you can see how these values and this equation turn into this. And now to get this in, so I said this is an equation, not the equation. Normally when I say the equation, I mean to write it in standard form, or I guess general form is really what it's known as. So let's do that. Let's distribute some things here. So 2 and 4 distribute each. So we get z minus 3 is equal to 4x minus 4 plus 2y minus 2. We can move things around to get, trying to think of a good way of writing this. Let's write it like this. Let's write it as 4x plus 2y minus z. So subtracting the z to that side. But then notice these two combine to negative 6, but if you add 6 to this side, 6 minus 3 is 3. So I'm kind of rearranging it in this way, but I'm going to leave this as our answer. So this is an equation for the tangent plane, the plane that's tangent to this elliptical paraboloid at this point. And if you wanted to use a graphing utility like quick graph, for instance, to graph this equation and this equation, you'll indeed see that at this point, 1, 1, 3, this plane will be tangent to this curve. So that's a really nice exercise, I think, for everyone to try. But now, this follow-up question asks the following. It asks us to use the above result to approximate this value of the function. So f of 1.1 comma 0.95, and then afterwards we're going to compare to the actual value of this by just plugging in these x and y values to see what the z value is. So that's going to be a little bit of fun. Let's take a look to see if we can do that. Now, what do I mean by use this result to approximate? Well, if you remember from Calculus 1, if you have a function, f of x, on the xy plane, and you consider a tangent line, which we normally call L, so this linear approximation function is just the function of a line. We usually call this L of x, something like that. And this is at a particular tangent point of tangency, whose x value we usually call a, and then you can pick an x value that's close to a and plug it in, and what you'll notice is the distance between the tangent line and the function will actually be very, very close. They're not too far apart. The closer the x value is to the a value. So the closer your value, x value, is to the x value of your point of tangency, and the closer that your outputs will be actually. So notice 1.1 and 0.95 are pretty close to these x, y values 1, 1. So with that being said, hopefully if things line up correctly based on what we saw in Calculus 1, then plugging these values into the tangent line and solving for z, tangent plane, and solving for z, will give us a value that's pretty close to actually plugging these directly into the function itself. So let's compare them. So if we plug those into our L function, first off, how do we call this an L function? Well, here this was L of x, so our function now is going to be L of x comma y. That's the linear approximation function, and it's just solving for z in this equation. So notice if you just subtract 3 and add z to the other side, you'll get z is equal to 4x plus 2y minus 3. So I think that's a good place to kind of start that approximation. And now we want to find L of this. So what we're going to say basically is the following. Since 1.1 and 0.95 is close to 1, 1, which are the x and y values of the point of tangency in this case, that means f of 1.1, 0.95 is approximately equal to L of those same values. So the inputs 1.1 and 0.95. So we're going to actually plug them in. So notice 4 multiplied by 1.1 is 4.4 plus 0.95 times 2. Well, let's see, 0.9 times 2 is 1.8. So 0.95 times 2 is 1.9, I believe. And then minus 3. Now I know that 4.4 minus 3 is 1.4. And 1.4 plus 1.9 is 3.3. So this is the value we get for our approximation. So I'm going to box that, and now we're going to compare it to the actual value. So this is our approximation. So I'll write approx next to it. Now the actual value, well, we plug into f directly. So f of 1.1, 0.95, I think we may need to use our calculator off to the side, but let's see. We get 2 times 1.1 squared plus 0.95 squared. Yeah, I could try to attempt to do this by hand, but 0.95 squared I think scares me a little bit. So I'm going to use my calculator here and let's see what we get. Okay, so all in all, this ends up being 3.3225. It's exactly that actually. So it's exactly 3.3225. So this is the actual value. And if you compare them, notice they're actually pretty close. They're actually the same as far as approximating to 1 decimal place. So that's not too bad. Let me label this as the actual value. So indeed, this idea of linear approximation holds, and that's really all I want to say as far as linear approximation goes. There's a little more to discuss because if you don't remember in Calculus 1, we discussed linear approximations and from there differentials. We'll still discuss differentials right now. So you can use differentials to talk further about linear approximations. I don't know if we're exactly going to do that, but we will definitely discuss differentials in 3 dimensions. In other words, over functions of 2 variables. So let's discuss that right now. Okay, so here for a differentiable function z equals f of x, y, we define the differential, sometimes known as total differential, as the following. So this is dz, and we say dz is equal to fx of x, y times dx plus fy of x, y times dy. Now, if you remember what this, of course, is analogous to from Calculus 1, this should actually make a lot of sense. So what I'm kind of trying to compare to is the following. So imagine we have the xy plane, and we have some function f of x, and we're considering the slope of the tangent line to be dy over dx. So if we consider this tangent line at this particular point of tangency, then we actually get that its slope, m, is dy over dx. And if we treat dy and dx as numbers, then, well, it makes sense because its slope really is a fraction of 2 values. Slopes are ratios after all. And if we actually compare to 2 points on the function itself, we actually have this distance, delta x, and then we have this vertical distance between these 2 points on the function, and the distance between these 2 vertical points is known as delta y. Now, something that you may notice, of course, is that the actual distance here, notice that is not delta y. Delta y is the total distance between the vertical values of the points. But what certainly is true is if you look at this small little triangle here, this is delta x. You can also treat it as dx. So you can think of it as being equal to dx, where this little change here is dy. Why does that make sense? Because really this is a triangle representing the slope of the green line, and for a right triangle representing the slope of a green line, or any line for that matter, rise over run is just the vertical distance of the triangle and divided by the horizontal distance of the triangle. And since our slope is dy over dx, then we get that. And in fact, since the horizontal distance is the same for the points on the green line or on the black curve, we get delta x is equal to dx. Okay, so that's actually a pretty important idea, and as it turns out, since we're kind of considering these in terms of fx to z and fy to z, really we're kind of considering this image twofold. We're considering this image on the xz axis, so imagine replacing these y's with z's, and also on kind of like the yz axis. Now it's not necessarily that axis itself, but it's an axis that's parallel to those axes. So it's something you can kind of think about a little more if you were to go to the point in three-dimensional space and kind of bring a plane that's parallel to the xy, or I guess it would be xz and yz axes. You'll kind of see what I mean. But this image nonetheless is pretty important. So what I'm going to do now is, well, I guess I can kind of explain. For differentials with one variable, we get the following. The dy is defined to be f prime of x multiplied by dx. So this kind of explains why this statement is kind of true. In fact, there are a few different ways of thinking of this. Notice if you divide by dx, which is often thought to be the derivative of x itself. If you were to divide by dx, dy over dx is just f prime of x. Now in this case, if you were to divide by dx here, you get dz over dx is equal to this. This would be 0 because derivative of y would be 0 with respect to x if you're taking the partial. Similarly, if you wanted to find fy by dividing dy to the other side, assuming x is constant, then dx is 0, so this all goes to 0 as well, and you get dz over dx is actually this. But it's the partial instead of the, it's the partial instead of the actual d values. So it looks a little funny. In fact, I was just looking at my notes here because we often obviously refer to this as partial f, or I guess you can call it partial z because z is f of x. There's partial z over partial x, whereas this is partial y over partial x, or partial z over partial y. There we go. That's a y, sorry. Okay, well in any event, let's kind of cut to the chase with this example here. So here we have this given function of two variables, z equals x squared plus 3xy minus y squared. And we want to find these two different things. This last one's a little bit of a conversation. But the first one's pretty simple. We want to find the total differential dz. So to find dz, first we need to find, well, the partial with respect to x and then the partial with respect to y, which I'll do up to the side here. So partial with respect to x is just 2x. That here the x drops, so you get 3y, and that goes to 0 because y is a constant. So we get 2x plus 3y. Perfect. What about partial z over partial y? What is that? Well, here x squared goes to 0. Here the y drops, so you get 3x, and then that becomes negative 2y. So this is 3x minus 2y. So they look kind of similar, but a little different. Okay. And with that being said, well then dz is just equal to the following. Partial z partial x multiplied by dx plus partial z partial y multiplied by dy. And that's all I'm going to say as far as this part goes. Perfect. So now this next question, this is where things get a little hairy, but keeping this idea in mind that delta x can be thought to be dx, and very similarly in 3 dimensions, delta y and delta x can be thought to be, delta x and delta y can be thought to be dx and dy respectively. So if x changes from 2 to 2.5 and y changes from 3 to 2.9, so there's an increase here and a decrease here, we want to compare the values of delta z to dz. Now delta z we haven't really discussed, but it's just what you would think of it to be. It's the change in z values between plugging in these y values and plugging in these y values. Okay, so just to be safe, I'm going to actually erase this, lift this up, and continue the problem. All right, so I lifted things up like I mentioned, and the first thing I'm going to do actually is calculate dz. I think it's a little easier to discuss what dz is. So dz, notice, is going to be, well, it's 2 times x plus 3 times y times dx plus 3 times x minus 2 times y times dy. Now you may ask, well, what are these values? What is xy, what's dx, and what's dy? Well, since x is changing from this value to this value, from this value to this value, and y is changing from this value to this value, the original values of x and y before the change are the values that we're going to plug into our function. So in other words, our x values will be 2, and our y values will be 3. That part I think makes sense. If you just kind of compare to how, the language is, we're changing from this x value to that x value, and from this y value to that y value. So we're looking at a small change from these points. So these are our original inputs. Now, the change, the actual amount that we're changing are our delta x and delta y. But remember from our previous conversation, in this context, we're actually letting delta x be equal to dx, and similarly, we're letting dy equal to delta y in this case. Because these are the changes of our inputs, which corresponds to the slope, and they have the same actual horizontal changes, if you will, in each particular line. The vertical changes, though, altogether will amount to what dz is, but we'll discuss that in a moment. Now, here dx, again, is the same as delta x, which is the actual change. So we're going from 2 to 2.05, so 0.05 is the change here. Similarly, since this is an increase, we consider the change to be just the difference between them, from what we went to from where we came from. So that's 2.05 minus the original one, 2. So this is 2.05 minus 2, that's how we got our 0.05. Perfect. With that being said, what would delta y be? Well, delta y would have no choice but to actually be a negative value then, because delta y would now be 2.96, the new value, minus the old one, 3, will give you a negative 0.04 actually. So here delta y is negative 0.04. I hope we can see this. It looks like it cuts off a little bit, so let me move the camera. Sorry about the slight shakiness there. It looks okay. So that means our delta y now is actually going to be a negative 0.04. So it's a little bit of calculation, but I think we can do this. Let's take a look. So it's 4 plus 9, so it's going to be 13, times 0.05. Okay. And then this is 6 minus 6. Oh, that's 0. Look at that. So we got lucky there. Now I know half of 13 is 6.5, so a tenth of that will actually be 0.65. So there we go. That's our dz value. Now I want to compare it to delta z. Delta z is literally the change in the z values. So delta z is going to be the difference of f when evaluated at the new x and y values, 2.5 and 2.05 and 2.96, from, or I guess minus, f evaluated at the original ones, which are 2 and 3. Okay, let's see. Yeah, so plugging in 2.05 and 2.96 into this is a little bit of a mess, so I'll do that off screen. But for right now, I'll at least leave some space here and I'll handle this one. When you plug in 2 and 3 into the original, well, you get 2 squared plus 3 times 2 times the y value, which is 3, minus the y value squared. So all in all, this is 4, plus 3 times 3 is 9, times 2 is 18, so that's 22, minus 9, 22 minus 9 is 13. So it's this minus 13. So hopefully this delta z will be close to dz in the case that this will be a little bit bigger than 13. So my guess would be 13.6 or something like that. So I'm going to do that calculation off screen and let's see what we get. All right, wow, so it's actually pretty dang close. So I got 13.6449. Look at that. That actually is very, very close to 13.65, which we thought it would be, just based on the idea that these values are pretty close to the original xy inputs, so the delta z and dz value should be pretty close as well. So in fact, the actual delta z value in this case is 0.6449, and if we compare that to the dz value we got, which was easier to calculate, we didn't need to use our calculator at all there, and that's kind of the main, I guess, argument for linear approximation and why it's more useful to use linear approximation to evaluate certain functions at particular values, because to plug into a linear expression is easier than plugging into a nonlinear expression. Now this is a pretty simple nonlinear expression because it's quadratic, but for all we know it could involve square roots or something crazy like that, or even sines or cosines. So yeah, But regardless of the linearization, which would be, again, a linear function, kind of, so there's no powers of x and y, which would, again, represent the equation of the tangent plane, then the calculation will be, well, easier. Anyways, with that being said, I think that's all I wanted to say as far as our conversation goes with tangent planes and linear approximations. There is a little bit more we could have discussed when it comes to functions in more than two variables, kind of like we have seen from the previous sections, but I'll leave it on your own to look into that, and it's pretty analogous to what we have been seeing. So imagine, like, for example, dw would just be the partial of x, y, and z in that case, multiplied by dx, dy, and dz, respectively. And in fact, you can kind of see how that would expand onto, beyond that many variables. So anyways, hope you enjoyed this. Really, really hope you enjoyed this. I know I certainly did, like I always do. And I'll see you in the next videos where we, again, go a little bit beyond, and it's going to be fun like always. So thanks for watching, and I'll see you then.